Okay, let's imagine that we perform a change of coordinates from, we'll perform a change of coordinates from x mu to x primed mu. And let's imagine that x primed mu is related to x mu by a Lorentz transformation, okay? Well, then we know that d4x will be equal to d4x primed times by the Jacobian. And because this is a nice linear change of variables, we can work out what the Jacobian is. And the Jacobian is related to, let's see, it should be an inverse of this matrix lambda, okay? So check that you can prove to yourself that the Jacobian is the inverse, the determinant of the inverse of lambda. What I'm going to do is I'm going to work out the determinant of lambda itself. So remember what lambda looked like. Let me just remind you. I'm going to think about a boost along the x direction, okay? You can think about a much more general Lorentz transformation if you like. And the conclusion that we'll come to is very general. So if you work out what is the determinant of lambda, well, you'll be able to check that you'll end up getting cos squared minus sinh squared, which is 1. So the determinant of lambda is equal to 1. The Jacobian is the determinant of the inverse of lambda, which is 1 over the determinant of lambda, and that's just 1. So that means, and this is something that we in fact already argued for a bit earlier today, is that d4x is actually a Lorentz invariant measure. Okay, good. Now, this is not just for the 4 vector x. If you have some other 4 vector, for example, let's say we were integrating over the 4 momenta. So this would be dp naught, dp1, dp2, dp3. This would also be Lorentz invariant by exactly the same argument. Just go ahead and calculate the Jacobian, and you'll find the Jacobian is 1. So this d4p is a Lorentz invariant measure. Okay, but in fact, this is not what we want. We don't want to do integrals over d4p, and let me explain why. So you know that if we take p mu, that will be Lorentz invariant. It's a contraction of 2 4 vectors, so it's Lorentz invariant. And I've already told you what this is equal to. It's equal to m squared. Well, if I write out what is p mu, what is this equal to? So, by the way, we often call p naught to be the energy, and p vector would be p1, p2, and p3, okay? So I will often use this notation in the blue box for the components of the energy momentum 4 vector. So in particular, p mu equal to m squared. If I just write out what is p mu, it's E squared minus P dot P. And remember, I've set the speed of light equal to 1. So that means that if you tell me the spatial momentum of my particle, I already know what energy it's got. So often I won't want to integrate over d4p. I'll only want to integrate over the spatial components of p, and I would like to know how to do that in a Lorentz invariant way. Okay, so let's start off. Let's derive the Lorentz invariant way to integrate over the spatial momenta. So let's start from d4p, which is dp naught, dp1, dp2, dp3. This is definitely Lorentz invariant. Now, let's take this measure. So I'm going to write it as dp naught d3p. So d3p is just dp1, dp2, dp3. And let's multiply this by a delta function. And we'll multiply by delta of p mu minus m squared. Well, that delta function only depends on p mu, which is a Lorentz invariant. So that delta function itself is a Lorentz invariant. So this is also Lorentz invariant. And now let me study what happens when I integrate dp naught d3p of delta of p mu minus m squared. So I am going to integrate over p naught. So I'm only integrating over p naught. Well, when I do that, I am adding up a whole lot of things that are Lorentz invariant. So again, this is going to be Lorentz invariant, okay? So whatever I'm going to get is going to be a Lorentz invariant quantity. So let me calculate that now. So I've got an integral dp naught. I've got d3p. Then I've got the delta function of p naught squared minus p dot p minus m squared. And I want to introduce a little bit of notation. From now on, I'm going to call omega p to be the square root of p dot p minus m squared. Okay, that is always what I will write. Oh, let me just tidy this formula up a little bit. These brackets are certainly not needed. Good. And now I can write this as an integral dp naught d3p, and we've got delta of p naught squared minus omega p squared. Good. Okay, so I want to do the integral now over p naught, and we know enough about working with the delta function to know that the integration measure should be the same variable as the variable sitting inside the delta function. So let's write this as an integral dp naught squared over 2p naught. So make sure that what I've written down there is just dp naught, okay? You should be able to do that. We've got an integral d3p, and we've got a delta of p naught squared minus omega p squared. So where is the delta function satisfied? Well, the delta function will be satisfied when p naught is equal to omega p. So if I do the integral everywhere where I see a p naught, I should just plug in an omega p, and then I've integrated over the delta function. So this will give me an integral d3p over 2 omega p. And this now really is a Lorentz invariant measure. So if I want to integrate over the spatial components of the momentum, if I just integrate d3p, that is not Lorentz invariant. So d3p is not Lorentz invariant. And if I integrate d3p and some other inertial observer integrates d3p primed, we're not doing the same integration. But if I integrate d3p over 2 omega p, and the other observer in another frame integrates d3p prime over 2 omega prime p, we are doing the same integration because we've got a Lorentz invariant measure. So this is how we're going to do our integrals. In fact, let me tell you what our Lorentz invariant measure is. I'm going to change it slightly. I'm going to take d3p divided by 2 omega p. So this is the Lorentz invariant answer. And then I'm just going to also divide by 2 pi cubed. So this is going to be our Lorentz invariant measure. Now, the reason why I am dividing by 2 pi cubed is that when we eventually get to the Feynman rules, there's going to be 2 pi's that fit in various places. We're going to work out our conventions for the 2 pi's in such a way that you are never going to make a mistake with where 2 pi's go in the final answers. And our convention is going to be every dp comes with the 1 over 2 pi. We've got d3p, so this is going to be divided by 2 pi cubed. Good, so that's going to be how we integrate in a Lorentz invariant way. Now let's talk about the normalization of states. In non-relativistic quantum mechanics, if you had a state of momentum p and another state of momentum p primed, you would normalize this to the Dirac delta distribution, delta of p minus p primed. But D3P is not Lorentz invariant, okay? We know D3P is not Lorentz invariant, and that means that delta of P is not Lorentz invariant. So in fact, this is not a good normalization for states for us. If we want to make D3P Lorentz invariant, we must divide by 2 omega P. We know the delta function and the measure transform oppositely. We just reviewed that. So if we want a Lorentz invariant normalization, we should multiply the delta function by 2 omega P. Remember, the delta function, the measure always transform oppositely. So if we need to divide the measure by 2 omega P to get something that's Lorentz invariant, we need to multiply the delta function by 2 omega P to get something that's Lorentz invariant. And we will again put in the 2 pi cubed, and this is again going to be to get the Feynman rules, the 2 pi straight in all of the Feynman rules. And this is now a Lorentz invariant normalization. So inertial observers that normalize their states in this way, in any Lorentz reference frame, they're all doing the same thing. So by using this Lorentz invariant normalization for the states and the Lorentz invariant measure, we're going to be able to make sure that the description that we have is manifestly Lorentz invariant. That's going to be a very big advantage. So that completes the ideas of chapter 3. The only thing I want to do next is to give you a few hints for the exercises that you're going to be completing.